This is the first of at least a couple, maybe three, maybe four videos dealing with polynomials. Polynomial can be defined as a finite sum of monomials, but that of course requires you to know what a monomial is. A monomial basically is what you would get by just multiplying and raising the powers, and actually multiplying would take care of it, so you don't even need raising the powers necessarily, where you're dealing with numbers and or variables. So a number would be a monomial, a variable would be a monomial, x is a monomial, x times x, which is x squared, is a monomial, 5 times x squared is a monomial. As long as you're just multiplying things together, we're interested really in monomial functions, polynomial functions in one variable, but you can have polynomials where there's more than one variable. So you could have something like xyz, that would be a monomial also. And if you take any monomial and you add it to another monomial, what you're dealing with now is a binomial. And then if you add another one on there, you got a trinomial, another monomial, three monomials, sum to a trinomial, and so on. You certainly ran into some of this terminology in a previous math class. A nice general definition of polynomial in one variable is what I've got here. P of x equals some number, call that the lead coefficient, a sub n, times the nth power of x. And this is in decreasing order. The powers are getting smaller as you look at it from left to right. We have the nth power, the n minus first power, which is one smaller. Then the one after that would be the n minus 2 power, and it keeps going down until you get to the very end. Last few terms would be a squared term, a first degree or linear term, and a constant term, which has no x in it. So we actually have n plus 1 terms here altogether, potentially, but we don't necessarily have all of them in any one polynomial. You have to have at least one term. That term could be a constant. The 3 dots in here, of course, means we're leaving out some stuff in the middle. And this is just meant to represent all the different possibilities for different powers and different degrees of the polynomial. If you have a third degree polynomial, that has to have n equals 3. So there's an added condition here. I didn't write in this last sort of condition, which is that a sub n is not equal to 0, because if it were equal to 0, then it wouldn't be nth degree anymore. So we have at least that a sub n lead coefficient and an nth term, though n potentially actually could be 0, but a sub n is not 0. And you just have a constant function like p of x equals a sub 0. P of x equals 5, for example. That constant function is really a polynomial function. Though we're not too terribly interested in it because constant functions are not very exciting. Not a whole lot going on there. Okay, so back to what I started to say about the third degree or cubic polynomial function we have here. If this were written as a negative 2x squared plus 15 plus x plus 7x cubed, it would still be a third degree polynomial. This one is written in descending order. The powers are getting smaller as you go from left to right. Third, second, first, 0th, or constant. And notice we have 4 terms here. A linear polynomial will have at most 2 terms. It has to have at least one term. It has to have an x term. The number in front of the x here, negative 12, is the lead coefficient. The lead coefficient in the p of x up here is 7. And in both cases, the lead term is the thing that's written down first. If I rewrote this q of x as negative 217 minus 12x, the lead term would still be negative 12x. It would just be written in the wrong place. So lead term, lead coefficient, that's always referring to if you were to write the thing in its descending order. if we're not in descending order, maybe just wouldn't use the term lead coefficient since it's kind of confusing, but it's always understood that we're in descending order when we talk about the lead term and the lead coefficient. That terminology is important, so make sure you understand what coefficient is, number in front of the x. And so the a sub n minus 1, a sub 2, a sub 1, a sub 0, and the ones that aren't shown here in the 3-dot ellipse, all of those are just real numbers. You can have complex numbers, but we're not going to be dealing with complex coefficients on our polynomials, so don't need to think about that. Okay, so in this particular video, we're going to concentrate on the end behavior, sometimes referred to as the global behavior. That's what you would see if you're looking at the polynomial from a distance. So we're interested in what's happening as the values of x in absolute value are getting really big, as they're approaching infinity. So if x is a billion, or if x is a trillion, or if x is negative a quadrillion or something like that, that's the end behavior. What's happening as you go to the right and look at the graph, or as you go to the left and look at the graph. I'm going to be talking about directions here, and try to be clear about what I'm talking about. But mainly we're interested in, is the function going up as you look at it to the right, or is it going down? And if you look at the function as you're moving to the left, is it going up or is it going down? That's the end behavior. It can be a little bit confusing because, of course, the standard for reading functions is we read them from left to right. So you wouldn't look at a function normally from the perspective of what's happening as the x values are decreasing, as the x values are going to negative infinity, or as the function is going left. But in talking about the end behavior, that's sort of understood that that's what we're talking about. That we can go right or left. Well, it turns out that the end behavior is completely determined by just two things. First of all, the degree of the polynomial, and second of all, the sign of the lead coefficient. So in this particular case of p of x, for example, the degree of the polynomial is third, and it turns out the most significant thing about that is that 3 is an odd number. The reason that's significant is because that means that for a particular value of x, and for the opposite of that particular value, well, x cubed will be opposite in the case of the negative x value as opposed to the positive x value. And a similar thing applies to the q of x with the negative 12x. X and its opposite, of course, are opposite. And the other thing is the coefficient. It's not necessarily, it's the sign of the coefficient that's really important. The 7 here actually tells me that p of x is going to go up to the right and down to the left. The fact that I have an odd degree means that the ends are going to go in opposite directions. One end goes up, one end goes down. And in this case, the end that's going down is to the left, and the end that's going right is that's going up is to the right. So up right, down left. And in the case of q of x, the negative actually flips that relationship, just as we saw with transformations of functions where the negative sign will turn the whole thing upside down, reflects it about the y-axis. Well, same thing here. X, if x is going to the right, well, we're multiplying by negative 12, which is going to bring things down. Of course, you were familiarized with that back when you first learned about slope. The slope here is negative, it's going down from left to right. The 7 here is not the slope, but it plays a similar role that tells us, in this case, the polynomial function, the cubic function, is going to go up to the right. Now, the reason we know that the end behavior determines things, or let me say that the reason we know the end behavior is determined by really just what's happening with the lead term can be demonstrated here with this new function. So this is not the same p of x I had before. I wanted to give it a pretty good size degree here so that we can really think about what's happening here. So p of x equals x to the 10th minus 20,000 x to the 5th. Now, if you calculated p of 0, both of these terms would be 0, p of 0 is 0. One way of saying that is that 0 is a 0 of this particular polynomial function. Turns out it has at least one other 0 besides that, which you could find. It would actually be the 5th root of, all right, let's see. No, that wouldn't work. Yeah, the 5th root of negative 20,000 would be a negative number, which would be a 0 of this. So it has at least two zeros. Has at least two x-intercepts. Anyway, what I'm really interested in looking at here is the end behavior. So we're talking about end behavior. We're talking about the absolute value of x approaching infinity. X is going to the right or x is going to the left, and how's the y or the function value behaving? Is it going up or is it going down in those situations? Well, if we were to plug in 5 here, 5 to the 10th is 9,765,625. Just a bit shy of 10 million. 5 to the 5th is smaller, but we're multiplying that by this 20,000, so it turns out the 20,000 times 5 to the 5th, if I did this right on my calculator, works out to be well, just the 20,000 part, 62,500,000. So 62.5 million roughly, and it's negative because of the negative 20,000. If you combine those two terms, do the subtraction, we end up with about negative 53 million, and most of that is coming from the second term here. The coefficient here is significant for a relatively small value of the input. If the input 5 is kind of small, it turns out that the first term is not that significant. But if we look at the end behavior, that's talking about letting x become large. The input becomes large in terms of its absolute value. So throughout here, I'm talking absolute value. If it seems a little bit confusing at times, or it looks like I might be thinking about a negative. Well, it's the absolute value I'm really thinking of. Of course, as the absolute value gets big, then the number itself might be getting small if the number is heading towards negative infinity. But then its absolute value is getting large. So suppose we plug in a million, same function. P of a million is a million to the 10th minus 20,000 times a million to the, that should be a 5 there. Same function as before. Okay, so anyway, if you work this out, well, it's not necessarily all that meaningful to plug these numbers into a calculator because it turns it into scientific notation and you have to read the scientific notation. So to avoid that, I'm just going to go ahead and use properties of exponents, which of course is what scientific notation is predicated on. So a million is 10 to the 6th. So in both cases, I just wrote the million is 10 to the 6th. And then use the power rule and 10 to the 6th raised to the 10th power, 10 to the 60th, 10 to the 6th raised to the 5th power, 10 to the 30th. If you multiply 10 to the 30th by the 20,000, well, one way of doing that is to think of 20,000 as being 2 times 10,000. 10,000 is 10 to the 4th, and so that would make it 10 to the 34th. And could put this into a calculator, but it's going to tell me that the answer is essentially 10 to the 60th power. Because this, it turns out that 10 to the 34th, and actually I guess maybe 2 times 10 to the 34th, only works out to be about 26 times smaller than 10 to the 60th. or 10 to the 60th is about, I'm not sure if I said that right. It's about 10 to the 26th times larger. The numbers are so big that unless you're somebody that's maybe into astronomy or something like that, or where you really deal with immense distances, or maybe cosmology and thinking about really large windows of time, for people like me who tend to not deal with numbers that are all that big most of the time, it doesn't say a whole lot to me, but it turns out that 10 to the 60th is just so much larger than 2 times 10 to the 34th that the 2 times 10 to the 34th is totally insignificant. And that will always be the case for any polynomial, that the lead term eventually will become as much larger than the rest of the polynomial as you want it to be if you go out far enough away from 0 to the right and to the left. And that's really what the end behavior is describing. What happens as we move away from 0 as we head towards positive infinity and negative infinity. In this particular case, this is a 10th degree polynomial, which means that if I were to plug in -1 million, I would get very similar results here, at least for the lead coefficient, or lead term, rather. Lead coefficient is just 1, so it's not contributing much to it. P of a million is 10 to the 60th. P of -1 million would likewise be 10 to the 60th because we'd be multiplying an even number of millions, or 10 to the 6ths together to get there, or -10 to the 6ths to get there. As x approaches infinity, P of x approaches infinity. As x approaches -infinity, P of x approaches infinity. So the way you want to think about this, the first part here, x is going to infinity, x is going to the right, P of x is going to infinity, y is going up as x approaches -infinity. So if we're reading the graph from right to left, going to the left, P of x is approaching infinity, well, again, it's going up. This can actually be formalized into a couple of simple statements. I just looked at an even degree polynomial. But if you had an odd degree polynomial, if we went back and did an analysis with this, maybe changing x to the 10th to x to the 9th and doing some calculations, what you're going to find is, again, that this first term is very determinative in terms of looking at how big the numbers are. But the other thing you would find is that if we had x to the 9th here, well, then if you plug in a negative, this would be negative. So if we had P of a million in that case, we would have a million to the 9th. And if we had P of -1 million, we would have -1 to the 9th. And a -1 to the 9th would be multiplying an odd number of negatives together, which would give us a negative result. And so in that case, the P of x will go down as x goes to the left. Let me see. I think I changed this and changed it the wrong way. So you fix that. If the degree is even, the ends go in. Oh no, I had it. That's the problem with cutting and pasting. You need to read everything everything you pasted. Okay. If the degree is odd, the ends go in opposite directions. If the degree is even, the ends go in the same direction. And then to try to clarify what I mean by that, I'll maybe draw a picture. If the degree is odd, the ends go in opposite directions. What I mean by that is one end is going to go up and one's down. So you might have it going up to the right and down to the left. For this, you can think of a linear function. The degree is odd. And of course, the slope means that as you look at it from left to right, it's either going up or down. The ends are going in opposite directions. Now I'm leaving some space here in the middle because I don't want to suggest that anything is known about that, because the end behavior doesn't really deal with that. We'll have to look at that in a later video, the local behavior. Another thing which I should mention about polynomial functions, they are definitely connected. They're continuous. They're also smooth. Smooth essentially means that if you go ahead and zoom in and zoom in and zoom in at any particular point, as you continue to zoom in, you will get a graph that looks more and more like a line. A line is completely smooth. It never changes directions at all. Polynomials can change directions, of course, but if you zoom in enough, you don't really see that. So there might be some bumpy behaviors, some ups and downs in that, but as you zoom in, those ups and downs become less apparent. In more advanced mathematics, they just define this in terms of the fact that it has infinitely many derivatives, and you can just keep taking derivatives, and eventually those derivatives will all just become zero. And then once the derivative is zero, all the derivatives thereafter are also zero. Okay, so if it's odd, first degree, third degree, fifth degree, 27th degree, any of those, it's going to look like one of these two. And determining whether it's like the one I'm showing here, where the graph is kind of increasing. I don't want to say it's an increasing function because it may not be increasing everywhere. In a global sense, it is, but there are probably going to be some places, or could be some places, where it's actually decreasing in the space that I'm not showing here. And same thing with this one on the right here, which overall looks like a decreasing function, but keep in mind that we are leaving out the behavior in the middle, so that it could be increasing and then decreasing and decreasing up and down. But overall, from a global perspective, as you look at it from left to right, the function is decreasing. So eventually you'll get to a point where it's going to just keep dropping. That's true for any odd degree function. I also want to mention an odd degree for a polynomial function does not mean that you have an odd function. There are odd degree polynomial functions that are odd. There are no odd degree polynomial functions that are even. But the fact that the degree is odd does not mean that the function is an odd function. And likewise, having an even degree does not mean that the function is even. But it does mean it can't be odd. And that use of the language here, of course, can be kind of confusing, but that's true in language in general. It's not anything specific to math. Okay, so if the degree is even, the ends go in the same direction. So what I mean by that is either they're both going down, go down to the left and down to the right, and some stuff in the middle that we don't really know about, or it's going up to the left and up to the right, and again, although it will be continuous, there's no breaks, so I don't want to suggest that it's broken. Although there are no breaks, can't say in general what this part's going to look like. That'll have to wait for a later video. And let's see, okay, so that was the end of what I had written down here. I was thinking to possibly go to GeoGebra and look at some examples of this, but I don't think that's really necessary. I think that you should just do that on your own. Look at, we already know about linear functions, which look something like one of these two. We already know about parabolas, looks like one of these two. A cubic function, in terms of its end behavior, will be like one of these. A fourth degree will be like one of these, and so on and so forth. And I encourage you to go ahead and try a few functions on your own. So for example, we might look at this one. The fact that, I don't think I sort of danced around it, but never really came right out and said it. This one here, one end up and one end down, so that's going to be the case if it's odd. Well, the lead coefficient will tell you which one of these two situations we're dealing with, and same thing for the even degree function, which of these two situations we're dealing with. And really, you already know that because you know about slope and you know about the concavity of parabolas. You know that if the m, the lead coefficient for a linear function, is positive, you're dealing with this situation. So this is what you'd have if you have a positive lead coefficient. Go left out a letter. And if you have a negative lead coefficient, it's going to look like the sort of downward moving function we have here. And a similar thing applies here, positive for the even. So just 4 cases. You don't necessarily have to memorize them because if you really think about it, in each case, it'll come into your memory just by applying that. So you apply 2 things. Is it even? Is it odd in terms of degree? You get these 2 cases. Is it positive or is it negative in terms of lead coefficient? You get these 2 cases. And I just practice this. That's what all that homework's for. And not quite sure how long I've been talking, but I feel like I've said enough here for this video, and anything that absolutely needs to be said that wasn't said here could be mentioned in the next video. So until then.